Hello everyone, my name is Matt Hansen. I'm a Principal Solutions Architect with AWS Robotics, and I'm here today to talk to you about how to build a better robot faster with AWS and ROS. Our agenda for today is first I'll introduce you to AWS Robomaker. I'm going to explain to you what is ROS and explain some of the benefits and concepts. I'll talk to you about simulation using a tool called Gazebo. I will also dive into some of the robot software development cycle, and we'll go more into detail about how to use AWS Robomaker, and I'll give you a demo of AWS Robomaker before we end, and I'll give you lots of links and open source resources so you can find out more information. First, I'd like to preface this presentation with the problem statement, which is that building robots is hard. Building software and hardware and integrating the two when you have oftentimes different teams and different skill sets, and they both have to work in parallel and then integrate it all together in the end, can be problematic. You can, especially with the fact that hardware development can be slow and you want your software development to be very fast. It's hard to iterate quickly in software if you're constantly dependent on testing on hardware. And if you have setbacks, those can be very expensive. So AWS Robomaker and ROS are together going to help make building your robots easier. So AWS Robomaker is a service that provides enterprise-grade availability with built-in system checks and a managed ROS and Gazebo software stack, which gives you reliable simulation and makes it easy to develop, test, and deploy your robot software. Robomaker has 4 main areas of capability. It has open source tools based on ROS and cloud extensions for ROS. It has simulation. It has a development environment in the cloud and fleet management for deploying and updating software to your robots in the field. Today, we're primarily focusing on ROS and simulation in the cloud using Robomaker. Well, now you may be asking, what is ROS? I've mentioned it a couple times already, so I'll explain what it is. ROS is an open source framework that provides inter-process communication mechanisms, standard message types, robotic control and observation tools, hardware abstractions, and common algorithms for robot software development. You can think of ROS as a robot SDK that provides building blocks and tools to build your robot applications. Why should someone use ROS instead of writing their own software stack? Well, ROS is the product of many years of robot software developers iterating, learning, and improving. ROS provides loose coupling, which allows for parallel development and test of software components, hardware abstraction, which enables changing hardware without changing interfaces. ROS has an established community, which enables faster time to product by reusing existing code instead of having to write it from scratch. And ROS provides simulation interfaces, which provide the ability to test in simulation, which reduces your reliance on hardware in your development flow. Because remember, building robots is hard, and ROS makes it easy to reuse and extend existing software so that developers can focus on their own new algorithms, developing their hardware and developing for their users' use cases. Now that you've heard what ROS is and why you should use it, I'll give you a quick overview of some of the ROS key concepts that will help you understand ROS. First off are nodes. Nodes are processes that run on your robot and across your network that perform work. They can collect sensor data, plan responses to sensors, or control motors, for example. The ROS core is like a switchboard operator from the early telephone years that connects those nodes together. Messages, these are the data being sent between nodes on channels that are called topics. And topics are like TV or radio channels that have publishers and subscribers. Services are similar to topics and publishers. They're a client server pattern where you have a node that will make a request to another node and receive a response. And finally, ROS bags are basically a way that you can record and play back data that's, messages that are being published on topics or services. And this is useful for being able to play back for testing and debug. Here's a visual example of a publisher and a subscriber. First, the publisher registers with the ROS core to advertise that it's publishing messages on a topic. The subscriber also registers that it wants to subscribe to that topic. Once registered, the publisher will publish messages to the subscriber, and the subscriber can then take actions based on those messages when they're received. So an example would be that you have a publisher that is a camera node, and it is publishing video to a camera topic, and you have a subscriber that is receiving that video and then doing some type of analysis such as object recognition. There's two other common ROS communication modes. Services, which are used for synchronous communication. Those are useful for getting and setting state, within your system. So, for example, you can check to see if a certain piece of hardware is enabled. And then there's actions, which are asynchronous, and those are used for long-running processes. So for those, you send a goal location to a robot, for example, and then rather than wait, you do other processing, and at some point later in time, you get a response that says, I finished what you asked me to do. So here you see in the example that we've got a client node and a service node, and the client makes a request, and then the service node provides a response. And the main difference, as I mentioned, between services and actions is when that response comes, whether it's immediate or much later. So in order to standardize communication between nodes, ROS also provides standards for commonly used messages and topics. For example, if you want a robot to be able to move, two of the topics that you would use are the map, or two of the messages you'd want to send it are a map and a goal. So for sending a goal pose to a robot, you use what's called the move-based simple goal topic, and the message type is called a pose stamped. In order to send it a map, you use the map topic with an occupancy grid. And once you do that, then the robot can navigate to a goal location. And I'll give you an example of this later in our demo. One of the other benefits of ROS that I mentioned are that it comes with a standard set of tools. One of the key tools within ROS is called RViz, which stands for ROS visualization. And it allows you to visualize data that is being published to topics. So here you can see an example of a robot in the center with a map around it, and the light areas in the map represent free space that the robot has sensed, and the dark black edges along here are the areas where it's detected a solid object. And then the lighter red here is a representation of the laser scan that it's using to sense around it. So this is a simple example. And again, I will show you in more detail when I do the demo. Another key enabling technology within ROS is ROS launch. This enables you to spawn multiple nodes in parallel on a system or even across multiple systems. ROS launch is defined using ROS launch files, which are written in XML or in Python, and they contain all the information necessary to start a node or a whole system of nodes, including things like setting their parameters and passing them arguments. AWS Robomaker uses ROS launch to start nodes in simulation. No conversation about ROS would be complete without discussing ROS 2 as well. ROS was originally designed for use in the education and research communities, but quickly spread into products. Because ROS wasn't designed with production robot systems in mind, ROS 2 was born a few years later to address some of the gaps to production. For example, ROS 2 includes specific enterprise upgrades such as higher quality core libraries, enhanced security, improved determinism, real-time communication support, support for lossy networks, multiple OS support. It's now supported in not just Linux, but also Mac OS and Windows. It relies on an industry standard middleware layer called DDS. It has improved abstraction and a unified API across multiple languages, primarily C++ and Python. And lastly, ROS 2 provides a bridge that allows you to run a hybrid system with both ROS 1 components or nodes running and communicating with ROS 2 nodes, such that you can either run a hybrid system, permanently, or you can migrate over time your ROS 1 nodes into ROS 2 by basically as you migrate each one, then you essentially move it across the bridge. If you'd like to know more information about ROS 2 and about the newest release of ROS 2, we've written a blog, and you can see that on aws.amazon.com about the latest release, Foxy Fitzroy. Now that you've had an introduction to ROS, let's discuss simulation. ROS provides interfaces for simulation because, remember, I said building robots is hard. Testing software on hardware can be a development bottleneck, but simulation allows you to gain high confidence in your software before putting it on hardware. You can test hardware and software in parallel this way. And then you can even automate the testing of your software into your workflow to ensure that every new code change is working prior to merging it to your mainline. AWS Robomaker has enabled cloud-based robot simulation. With the power of cloud-based simulation and open source tools, we've enabled our customers to build better robots and to get them to market faster with fewer production errors. These are a few of our customers using Robomaker today. Milvis Robotics is an interesting use case I'd like to tell you more about. Milvis Robotics makes an UV disinfecting robot for hospitals, which is increasingly important and a rapidly growing application. Because of this growth, they needed to increase development velocity while improving quality and maintaining high safety standards. Real-world testing was challenging. They couldn't get access to real hospitals for testing, and building mock-ups was expensive and time-consuming, as you can imagine. This made finding software defects difficult and slow, but with Robomaker, they were able to run simulations in a virtual hospital environment, automate their testing, and speed up their development cycle. As a result, Goku Ertunç, the co-founder and CIO of Milvis Robotics, said, AWS Robomaker simulation helped us save money and time and eliminate obstacles to scaling our testing efforts. With Robomaker, we can forget about infrastructure and focus on development and testing. We implemented a Robomaker simulation CI and can now easily test our robots in different environments, resulting in a huge quality improvement. So here's a short video of Milvis testing their UV disinfecting robot in the simulated hospital world. The robot is moving around a hospital room with 3 hospital beds. The blue lines you see represent the laser scan it uses to sense objects around it as it disinfects autonomously. Now that you understand the benefit of simulation in general, let's take a look at the details of how to simulate a robot. And later in the presentation, I'll show you how to run a simulation in the hospital world. The Gazebo 3D simulator is an open source simulation designed for robotics. Its plug-in based design allows for different world and robot models, different physics engines, and interfacing to different robot communications protocols. Here is a sample 3D simulation of a hospital world with a rendered PR2 robot. The robot is in the hospital lobby with patients and staff, as you can see in the background. Note that this world is published open source on GitHub, and a link will be available at the end of the presentation. Now let's look a little closer at the simulation. The hospital world is created with a standard SDF, or simulation description format, which is an XML format that describes objects and environments for simulation. Within the world are 3D objects such as people and lobby furniture. These are also defined as SDF, with meshes overlaid for visual appearance. Finally, the robot itself is created in a special type of SDF called URDF, or Unified Robotic Description Format, which defines not just how it looks, but how it moves as well. Now let's take a step back again and look at the overall robot software development cycle. Software development, as you probably know, is an iterative process with multiple levels of testing. Simulation enables testing at the system level as part of the CI/CD flow, and then you can do your final testing on the robot hardware prior to a final release. Released code is then deployed to the fleet via over-the-air updates. So with simulation, you can decouple your hardware testing and your software testing so that you can iterate very fast on your software testing. So why AWS Robomaker? There are multiple benefits to running simulations in the cloud with AWS Robomaker. First is access to cloud scale. The service automatically scales the amount of compute required to run the simulation up to 15 virtual CPUs. In addition, you can scale horizontally by running hundreds of simulations in parallel with a single API call. Robomaker provides enterprise-grade availability with built-in health checks to ensure simulations run smoothly and reliably. The service is fully managed, meaning you don't need to worry about provisioning and running your Gazebo software stack, and only need to focus on running your ROS application. Robomaker is integrated with multiple AWS services, enabling you to easily extend cloud functionality like CloudWatch logs, ML services, data storage, and analytics services, and more to your simulations. Finally, with pay-as-you-go pricing, you only pay by the minute for the resources you consume. Here's a high-level view of the Robomaker architecture and the user developer flow in using it. Developers can use our IDE to create robot applications based on ROS. Then they upload them to S3 and simulate them in Robomaker simulation. They can then interact with those simulations using ROS tools such as Gazebo and RViz. They can also connect to other cloud services such as CloudWatch for logging and Kinesis for video streaming. Finally, they can deploy the code over the air to the physical robot when testing is complete. Now I'd like to give you a demonstration of running a robot in a virtual hospital world with AWS Robomaker. Starting from our browser, we're going to quickly create a simulation job using the Robomaker console. This is the Configure Simulation page, where you can set up your simulation job. We've set our simulation time limit to 1 hour, and we're using ROS Melodic as our ROS distribution, and an IAM security role I created called Robomaker Sim. We have the ability to also set a compute limit if we want, since Robomaker is billed by the sim unit usage per hour. We can also specify an S3 bucket for our output and use a VPC, a virtual private cloud, if we want. But we don't need those for this demo, so we're not going to use those. Finally, we have the ability to define some custom tags if we want for the simulation job. We'll click Next. And now we can specify a robot application, which is for putting code on a real robot. For now, we don't need that since we're just doing a simulation. We'll click Next and we'll create our simulation application. This is where we set up our simulation in Gazebo. I created a simulation application already called Hospital World Demo. Now we have to specify the ROS package name and launch file to use when starting the simulation. We then define some environment variables, including the initial pose, where the robot will be spawned inside the simulation. The pose here is just an X and a Y coordinate, and this pose that I've chosen will put the robot in the center of the hospital lobby. We can click Next now, and we can do a final review before we create the job. Okay, a quick review shows the simulation configuration, and scrolling down, we see the simulation application. The source file is the S3 location where I've stored the simulation application, which I pre-built for this demo. Everything's ready, so we can click Create, and it will start creating our job. This takes us to another screen, which says your simulation job was created. We see the job status shows as pending. Once the job is created, we'll see the tools appear so we can interact with the simulation. This typically takes 1 to 2 minutes, so we'll skip ahead until the job is running. And it should start running. Oh, there we go. Now that it's running, you'll see that there are now several tools available for us to use. We're going to open the GZ client tool, which is the GUI tool for viewing the Gazebo simulation. Now we're viewing the Gazebo simulation with a camera view. We can zoom out, rotate, and pan until we find the robot in the lobby. There it is. Now that we see the robot, now we can zoom out farther and get a view of the entire layout of the hospital. Notice that this world is pretty large and has dozens of rooms and beds with beds and hospital equipment, which just gives you an idea of the size of the space that can be used for testing. This enables you to test your SLAM, navigation, and collision avoidance algorithms, for instance. Now we're going to open RViz, the visualization tool. Now we are going to add some ROS topics that we want to view, starting with the robot model. You'll see the robot is now in the center of the grid. Now that we have the robot model, we're going to add the map. The map is just a 2D view that is being generated by running SLAM using the robot's LiDAR or laser scan. We have to set the topic name for map to /map. Next, we're going to add the pose that will be the goal location for the robot to move to. We set the topic name for that to move base simple goal. Finally, we're going to add the path that the path planner is going to create for the robot when we send it a goal. We have to set a topic name for that as well. Good. Now we're ready to send the robot a goal. Oh, I got a little ahead of myself. Now we're ready. Okay. Now we're ready to send the robot a goal. The robot is in the hospital lobby here with mapped empty space showing as light gray, as I mentioned, and the dark gray areas are unmapped. We're going to use the 2D nav goal button in RViz to set a pose as the robot goal. And we're going to send it to the room here at the bottom of the screen, which has not yet been mapped. You'll see the map update as the robot moves while it's running a SLAM algorithm. And then you'll see a green line that shows the robot's planned path. Now we're going to put Gazebo side by side with RViz so you can see both at once. You'll see the robot is slowly moving in the simulation on the left, and on the right you can see that the map is updating as it's moving. The map is being generated by the robot's laser scan, which is also published on a topic. So let's add that to RViz so that we can see that too as it moves. Okay, we're choosing laser scan as the topic, and then we have to set the topic name. As the display type is laser scan and the topic name is base scan. Then we're making it easier to see the laser scan by increasing the size of the markers to make them bigger. The red markers that you see there that are showing up are the walls and the obstacles that the robot is detecting. As you see, we can also change perspectives to see the robot at different angles as it's moving through the doorway, for example. And when testing the robot, we would normally write a script to send a goal or multiple goals in succession to a robot and make sure it reaches those goals by checking its position via other ROS topics. This type of testing is good for validating SLAM, navigation, and collision avoidance algorithms. And, for example, ensuring that the robot doesn't get stuck in the doorway. Once a robot reaches a room, it turns to face the direction we specified on the arrow. And now it's done. It reached the goal pose successfully. Keep in mind, this was just a small and simple example, but with automation, this type of simulation can be a huge time saver in your software development. That concludes the demo. I hope you enjoyed it. Another benefit of ROS is that it's easily extensible. AWS Robomaker has created ROS packages that can be used on a robot or in simulation to access other related AWS services, such as Amazon Lex for speech recognition, Poly for speech generation, because robots need to talk too, and Recognition for image recognition, and of course, Kinesis and CloudWatch, which I've already mentioned. The Robomaker team has created and published multiple useful open source assets to our GitHub repository. This includes the cloud extensions already mentioned that can be included in your application. And we've also provided multiple 3D worlds for Gazebo that you can use out of the box to accelerate your software development. For example, the hospital world you have just seen is one of those available via open source. You may be wondering at this point, where do I find out more information about all these useful tools and assets? Where do I learn more about ROS and Gazebo? So here are some useful links that you can use to dive deeper into ROS and Robomaker. Thank you very much for your time today. I hope you enjoyed this overview of how to build a better robot faster using ROS and AWS Robomaker. If you have more questions, you can email to robomaker-contact-us@amazon.com. Please complete the session survey. Thank you very much.